Okay, we are having our lesson on analog versus digital. Okay, so let me bring you to Ajax Cinema. I always start that lesson with that. Okay, so we're going to go on Kingston right here. I want to show you guys a, a sort of a sign on the side of the road there. This is the school's laptop. It's not very fast. And it keeps doing this when I drag my little guy. Okay, so I'm trying to go around here. Right here. I'd like to be on this side of the road. There. Perfect. Now, am I able to see this here? Look what it says. Every time well, now I don't because I know it's there. But the first time, couple of times I saw that first when I started working. It's been there since I've been working at JCar, so like 14 years now. This has gotten me to laugh because it makes no sense. You cannot have digital sound. Why? Because digital sound would sound like this. So I was just trying to find a sound of a modem. So you guys should hear this. So do you hear this in the background?
Modems, dial-up sounds. The nostalgia is high. Back in the...
Okay, so not this guy. There's got to be a better one. Sound. I just want to have the sound. Come on. Oh, it's slow, this computer. Maybe this one? Let's listen. There we go. So, in university, this is how we were going on the internet. So what is this? So this is the modem trying to talk to the ISP, to the Internet Service Provider. And there you go. That's a good example. And that doesn't sound like anything I'd like to listen a whole movie through with, right? So what does that mean then? Okay, so this, what we just heard, is what digital sound would sound like, because it is digital sound, literally. So it's complicated, okay? So this is what I'm trying to explain today. Um, it's so different teaching on a computer like that. Well, I guess let's define analog versus digital. So I'll go on draw, okay? And we'll start drawing. Okay, pencil. Okay, so you guys should take notes. Where's my cursor? Here. Okay, so we'll have analog on this side. We'll have digital on this side. Okay, so analog, essentially, it's a wave, okay? All right. So, and digital is just a bunch of pulses on a single wire. Now, the spacing can change and so on, okay? Now, where is it? Here. Now, this here, when you listen to music, for example, this is what your eardrums are picking up, okay? So it's a change in air pressure. There's no sound in space, right? Because there's no air, right? So you can't have sound. So all the Star Wars explosions make no sense because there's no air in space, right? So you shouldn't be able to hear it. Now, if you're inside a spaceship, but you're in space, can you hear another spaceship explode? I'm not sure. I would have to think about that one. That's a good case. But anyway, this here, what's important to notice is that your signal is moving within a range. Okay, so there's a whole range, and the values that it takes are within this range. Well, this is just like your ears, right? There's no difference to that, right? And this is why you don't want to be by a jet turbine when the planes are lifting up, right? When they're leaving the tarmac, because it will make your ears bleed because the signal coming from the turbine is out of range, right? So literally your eardrum inside, right, vibrates more than it can handle and it just ruptures. So I don't wish that on anyone. Okay. Oh wait, when I was playing in my bands with my bands, like too often, this is why I have a ring in my ears at night, right? Like actually, I hurt my ears playing in my bands when I was younger. Don't do that. Okay. It didn't bleed, but I remember one time it hurt real hard. Um, Now, digital, here we need to talk about this for a couple of seconds. So as the pulses go. Okay, so picture a wire, right? Like just a wire. Okay, like a good example because you guys are familiar with that. So I have to take examples that make sense for you guys, like an HDMI cable, just connecting your Blu-ray to a TV, right? So if you look at an HDMI cable, I don't know that standard well, but there's a lot of pins, right? There's like 20 pins, right? HDMI pins, right? We'll be able nine. Did I say 20? Man, I was right on. Right? So all of those are digital. Now, do they have actually analog signals on those? I don't know. I don't think so. So see, I know nothing about these here. TMDS. I'm assuming this is all video. There might be some sound. I'm not sure how the HDMI standard works. I've never looked into that. There's so much to learn about, right? Anyway, that's something you guys could give me a bonus assignment on this, okay? But I know the sound is transmitted digitally on this. That I know, and so is the picture, obviously. This is why HDMI has taken over, right? It gives you a really sharp picture because it's digital. So where was I going? Just saying that on each of those wires, when you're playing a movie or a CD, whatever you're playing, or a game, right? It's sending a bunch of ones and zeros on this cable, and this is what we see here. So when I'll be drawing something like this, what I mean is that on this cable, there's a 0 volts, that's here, and then all of a sudden, now again, don't quote me on the HDMI because I don't know how the standard works. I could talk about older technologies, but let's assume it works on 5 volts. It could be less, it doesn't matter here, right? So all of a sudden this wire, if you had a meter on it, it would jump to 5 volts, right? As you measure the wire, but this is a bit here, right? But you can have also a bit being 0. That totally works. So that can be also a bit. So an absence of information can be information, if that makes sense. Okay? So I'm hoping this makes sense. Okay, so you have a wire. In the case of the HDMI, you get 19 pins, so 19 wires, and on each of them, there's bits being sent. Now, this is super fast stuff, right? Like, this goes like, I don't know again how fast it's going on the HDMI, but it's pretty fast. It goes even faster on optical cables, connecting big cities, right, for the internet and so on. But anyway, the point is, you got 1, so this would be a 1. This would be a 0, right? So this here is a 0. This here is a 1. Okay, good enough. Notice there's no in-between values, right? It's 1 or 0. Actually, you're going to either confuse the machine if you keep sending it values, signals that are in between. Like if you send it something at 2 volts, 3 volts, your TV will go like, what? Like, what do you want me to do with this, right? Like, it won't know. And you could actually break your machine by doing that. It's not a joke. I'm assuming the newer electronics is protected against that. But if you keep sending signals that are halfway, you might actually break stuff. I know it did in older electronics. Now, let's go back to analog. Notice how the range keeps being used, right? So if I zoom into this part, for example, here, right? Right? So you get a signal doing this, right? And notice how there's an infinite amount of range of values, my apologies, that it can take, right? Now I can zoom in further, and then I still have this, and I still have an infinite amount of values along the way here. So the way I like to sum it up for my students is that you can picture analog as being equal to the real numbers, right? So the real numbers in math, right, is equal to a number line, right, with say 0 and 1. And how many values are there between 0 and 1? Well, there's actually an infinite amount of values between 0 and 1 when you're in the reals. Now, what does that mean? Well, it's easy, right? So if I go at 0.5, what's the number just next up from 0.5? Is it 0.51? No. It could be 0.51, but no, it could be 0.1, but no, it could be 0.1, right? And so on and so forth, right? And so you can have an infinite, it just crosses through the range really quickly, right? Same on the other side of 0.5 here, right? So you can, is the next number down from 0.5, 0.49? No, it could be 0.499, and then 999, and then a million nines, and then you're still not at the number right there. By the way, those of you that will do your calculus in grade 12, this is exactly what derivatives calculations are based on. Okay, there's a lot of math in calculus that is based on exactly what I just said here. Okay, so analog has an infinite amount of values in a given range. It doesn't matter how small the range is. It could be 2 volts to 0 volts, right, in the middle, because this is minus 2 volts here. And in digital, well, you could compare this to the naturals. So those are equal to the naturals. So what's the naturals? Well, those are easy as well. The naturals are the numbers we learn when we're a kid, right? 0, 1, and then you go to 2, but there's no number in betweens. There's no like 0.5s and so on, right? Like fractions, right? So we go 0, 1, 2, and then you can go, well, anyway, let's not get into the negatives here. Okay, so does that make sense? Digital equivalent to the natural, so the symbol is a line and a capital N. And for the reals, it's the same. So line and then R's, like that. Okay, so these are mathematical concepts that are really useful. I get the sense I'm forgetting one thing on this. Well, we'll come back to it. Okay, so what is that? Why is that all important? Well, right. So if we go to here, so what did they mean here? Digital sound, right? What did that mean? Well, it simply meant that the way the information is encoded on the, now they use tapes, right? I've seen them, right? Movie tapes. I'm not sure how they're called, movie reels. Today's theaters, they're large, and so on and so on. But the sound is actually digital, right? So it's complicated. Again, it's on one of the sides, audio. Yeah, I'm not asking it the right way. Movie reels, audio track. There we go. Okay, so let's look at this, right? So I'm not a movie guy, okay, like a theater guy, so I'm not too sure about the amount of standards on those reels that exist. But I did remember hearing about this, that the sound is on one of the sides, okay? And then now here it's actually analog, but I know in the newer ones, and that's why the Ajax theater here was saying digital, is because on their reels, on one of the sides, now it could be this one, like sound on film, that sounds right, okay? They had the information in digital. And so this is what they meant. We still have a problem though. I'm hoping you guys are realizing this. It's all nice to have digital, like like the sound being encoded digitally on your track, but I can't listen to it because it'll sound like this modem, right? It'll sound like this. So how do we get from the information being stored digitally to analog? And an even more important question is, why do we use digital? So there's a ton of good and interesting ramifications to what we're just saying. Let's start by how we go from one to the other, I guess. Um, so I'll need to draw again. So let's create a new signal, a new page. Oh, come on, I don't want to save it. Just new, don't save. So what we're going to have is on one side, we have information that's analog. Now, this is like the mics, right? So, for example, when they film a movie, they use mics, right? And a mic is basically just a speaker, but inverted. We can talk about that another time, right? So picture a sound wave here, like what we just described. So it's got an infinite amount of values as it's going through a given range, right? It's going in a microphone. So why am I? Because this is sound here, right? This is sound. So you need some sort of transceiver, you could call it, right? So you need to transform. This is a physical signal. It's in the air. And you need to transform it into some electrical signal. And then this thing will transform it into the same waveform, but on a wire, right? So picture a wire having this analog signal on it. And then in the old times, like when I grew up, like man, I used dozens of tapes, right? Like cassette tapes, right? So it was all analog. So this was being put into using magnets, right, on a tape, and then you could listen to the music like that in a Walkman and so on, right? Your parents, they grew up the same, likely. Um, so how do we go to digital from this? This is my question to you guys. So we're going to use what we call a ADC. So you need to know about this. Okay, so this stands for analog to digital converter. And then what's going to be the output of this? So it comes in analog electrically, and then it's going to come out digital. How can we do that, right? So now, this is not a board like it's in class, so I'm going to have to use another screen in a couple of seconds. That's fine. So essentially what happens is, so I'm expanding here, right? I'm going to expand it here. Okay, what happens in the ADC? Okay, so the output will be digital. So a bunch of zeros and ones. Okay, what's going on inside? So you get the wave, right? And then it's going to go through this machine. It's a chip, right? Like they look, like I can show you examples if you're interested. A typical ADC chip. They just look like chips. Like there's nothing special about them, right? So here's an 8-channel. Okay, typical kinds of chips, okay? But those machines are so important, okay? They are really part of modern electronics. And that's why I like to teach about it. Like I'm trying to make it as relevant as I can to you for you guys. So what it does, it's actually pretty simple, okay? We could actually build one in class, okay? It would take quite a bit of time, but we could build one. I've never built one, but I know we could build one from scratch. Um, all it's doing, okay, is that as it's reading, as the electrical signal's coming in, this is assigning a range to this, right? It's giving, okay, so let's actually, whoop. So let's actually split that idea a bit more. So what happens is um, it takes a sample every so often in time. Okay, so time is moving, right? And this machine, what it does, it's giving for output the number value when it took its snapshot. And so if this is in volts here, right? And so pretend this is 5 volts, right? Okay, the tip here, right? Now it's splitting this in like thousands of numbers, right? Because it's got way more precision than what I drew here. But essentially what it's doing is, so say at time, say this is time t1, let's call it t1, right? So here it's going to give a number 0. And then as this, because this wave is going forward, right? So when it's a bit further down, now it's going to give this value, and say this is negative 100, right? I'm just making up numbers, right? Don't get confused here. When I say 5 volts, this is split here into thousands of tiny increments, right? So depending on the precision of the ADC you're using, the top value here might be, I don't know that by heart, but say 10,000, right? They're high values, right? So you can have a really fine grain precision here, right? So you can read really a lot of positions, right? And so on and so forth, right? So as this wave is progressing on the pins, on the output of this chip, it's going to give the value for every time position that it took a snapshot of, right? So, well, there's not much else to explain to it, okay? Um, and then these numbers are going to be transmitted digitally here on, depending on the ADC you're using. So the one we were showing here was a 10-bit, right? So using 10 wires, right, it will give information to represent numbers from a given range to the other extreme, basically. And so what happens is this, guys, this is the key part that I don't want you guys to miss, is that once your info coming out of an ADC is put digitally, right? So these numbers here that we had, these numbers here for every position, these numbers, when they are digital, you can store them, transmit them, you can do math on them. So when I was a kid, when digital started to really pick up, these were put on CDs, right? That's how it all started for us. That was put on CDs. Today, you guys, it's just straight down from the internet, and you stream videos and so on. Okay. Uh, in 10 years, some of the students, because you guys, your parents, they're not that old yet, but in 10 years, the students might not even know what a CD is. Like, they might never have seen one in 10 years, okay? So kids that are like 3 years old right now, like, CDs might become really rare because you guys are all streaming and so on. I'm not blaming anyone. I'm just saying it's changing, right? So, um, And the beautiful thing about digital is that information that's digital is, this is the key, is immune to noise. Okay? Immune to noise. Okay, so this is really scraggly. So what that means is I can send emails or even call someone in France, in China, in Japan, in Africa, in Brazil, wherever, and talk to them live with a bit of a delay, obviously. But the information is transmitted without loss. That's because the signals are clear zeros versus ones, right? Engineers over the years, and we're talking like 20 years, 30 years now even, we've been able to build circuits and signal processing machines and so on that are extremely good at sending super fast a gazillion of ones or zeros without losses over tremendous distances. So by satellite, by optical cables, by radio waves, it's on wires, and so on and so forth. Okay, and so technology has gone forward tremendously in transmission of digital information. The challenge is for analog, you cannot do the same. In analog, so for example, when I was a kid, when I liked an album from a band, I needed it to copy onto another tape. But every time I copied it, the sound quality would diminish, it would drop. It's the same as, I never tested that, but I can anticipate what would happen. It's the same as if I printed this page here that we see right now and went to a photocopier, photocopied it, and then took it, and then photocopied it again, and you get the idea, right? If I photocopied it 1,000 times, that picture would get probably all grayed out. And that's because we start from something analog. But copying information that's digital, stored all in zeros and ones, we have systems to copy this endlessly without losing a tiny bit of information. And this is the miracle of digital, of anything digital. And this is why when you guys stream, so I just registered on Disney Plus, right? And I'm a bit of a Star Wars fan. I'm not that much of it, but I don't mind them, right? So I wanted to watch The Mandalorian, right? I mispronounced that, right? So I had to go on Disney Plus. So I watched the first 3 episodes twice because I thought they were really cool. And in my house, I'm getting exactly the same digital information as anyone else around the world in all of the in the U.S., in Canada, France. I think they're starting Disney Plus now, and so on, right? But I had the exact same information as any other customer in the U.S. and or anywhere in the world of every single piece of the clips of the episodes. The sound is exactly the same as everyone else, getting the same file, the same stream, and it's truly wonderful. It really is a truly wonderful technology that we have now. Um, so I think it raises a final question. This is beautiful that we can send information digitally. So by the way, this is what they meant at the Ajax Cineplex here. When they said digital sound, this is what they meant, okay? Is that the sound is stored digitally. But the sound that you hear when you go to a movie is obviously not digital. So how do we go from digital back to analog? Well, you learned it. You guessed it. If we can have an ADC, analog to digital converter, all we have to do is get the other kind of chip. So it's called now a DAC, right? Actually, I'll try to squeeze it in here, right? So then what we'll use is a DAC. Now this is, I'm not going to write it, I'm tight here, digital analog converter. So you guessed it, what it's doing, it's taking those bits here, those numbers, right? All that information, and it is now converting it back to a sound waveform. In the case of video, it's the same idea, right? It would transform it back into colors, intensity, grace, shades, and grayscale, and so on. I think we'll leave it at that, okay? The only thing I'll add to that is when I was younger, when I was in high school, when I was your age, I was a bit of a hi-fi guy. So it was a bit of a passion of mine, and I'm still a bit into that. I just don't have the money to buy expensive gear. But hi-fi stands for high fidelity, and there people like that are still around, right? Like folks that will spend easily, you can spend 10 grand on just a sound system. You don't have a Blu-ray player, you don't have a DVD player, you don't have a TV yet. All you have is a CD player, an amp, and speakers, right? You can easily dish out 10 grand if you wanted with all the wires. And and people still believe the same on what I'm just about to talk about, is that digital, as beautiful as it is, with all its qualities, with all the it truly is a miracle in a way. Some people still swear by analog sound. So what would that be, right? So I'm thinking especially of the turntables, right? So the vinyl discs. Okay, so they're black. Okay, you get a needle, you get an arm, right? So picture an arm. There's a needle, and then the scratching sounds, right, of DJs, right, and so on. This is what it's coming from, right? You scratch the disc, right? This is what it's about, right? And then so this is turning here, and then picks out the noise. Some of the hi-fi purists, right? That's how they're called, right? They swear by vinyls, okay, by those discs, okay, and I've heard them. My brother has a setup like that, and it does sound beautifully mellow. And there's something about the sound when your system is all analog where it's more natural. Digital gives a bit of a plasticky metal quality to the metal sound. Now, some of you are listening to this going like, what does that even mean? You have to listen to both to understand. Um, anyway, we can talk more about this, but and it's an interesting topic, right? Because people today tend to think, I wouldn't be surprised you guys, some of you guys listening to this, think that people have this tendency to think that everything digital, because it's digital, that it means it's better. It's not quite true. Uh, the reason why digital has taken over is because we can transmit so much information so nicely for so cheap and so far, right? That's the reason why digital has taken over. This is why our phones work with a lot of digital on them. Okay, I'll stop here. We could take questions on that later on, okay? All right, so that'll be it for this lesson.